So now let's look at that last bit of stuff we did, which was 7D and scientific notation. And so a big part of 7D was that we were talking about vital statistics. And so vital statistics is, any kind of data we have concerning birth rates, death rates, life expectancies, those sorts of things. And so if you'll remember life expectancy, we looked at that chart to calculate, and life expectancy is the number of additional years we expect a person to live that's a certain age. And we know that that is an average, so some people would live longer, some people would live less, but that's what that meant, and that was the up and down column. Age was across that horizontal axis, but on that up and down, that vertical, it was how many more years we could expect them. And then we had travel risks. We calculated that, so we were often given a nice little table with a bunch of things in there, and we were asked to calculate the something rate per something else. So this is often accident rates, and so we put the number of accidents on top and then whatever we were asked to on the bottom. So it could be accident rates per billion miles, that would go down here, or per million hours flown, that could go down here. Or we were asked to calculate the death or the fatality rates with it. And in those cases, we put the number of deaths or fatalities, usually from a specific year, per whatever we were given. So the fatality rate per million miles flown, so we put the number of million miles flown down there, or per billion hours, whatever it is that we're asked. And do remember, if it's like the column says that that's billion hours flown, I could just put that number down there in place of billion hours flown and not put all the zeros after it representing billions. That's already been taken care of in terms of the units that are in the question. And then we talked about we worked those disease problems that have to do with some death rates. And in there we were really asked to calculate three major things. And so the first one I could think of is from that was we were asked to calculate the empirical probability. And if you remember learning probability, it may have been a way on back, we were putting the number that fits that scenario over the total number of basically scenarios. And so this is why this is sometimes easier to think of as a risk per person, because we will calculate this by putting the number of deaths by whatever disease it is they're asking us to focus on. So like the empirical probability of dying by kidney disease, so we put the number of deaths by kidney disease in the top. But this is per person, so in the bottom we would need to put the total number of the population, not just the total number of people that have died, but the total population on the bottom. And we generally don't write probabilities as percentages. This is not asked as a percentage, so you can just divide those two and be done. The next thing we're calculating there is they would say stuff like the risk of death by something is how many times greater than the risk by something else, death by something else. And so here, we want to know how many times, so we need to solve for how many times. Times is like multiplication, and so to do that we need to use some division. And so we set this up as just a different ratio. We put the number of deaths by whatever that first thing they mentioned by the number of deaths by the second. And so you'll notice, just like with percentages, this times greater is referencing B, and so the value from B, like the deaths by B, is what ends up being in the bottom of this. And then a slightly trickier version of a question here is they would ask us to calculate like how many people we would expect to die in, and then they would give us with an area that had a different population than what we started with. And we worked this really quickly sometimes in our notes. We just took like that risk, so that empirical probability, and multiplied it by the new population. Maybe easier for you to see what we're doing here is working with proportions. So what we have on one side, what we've already calculated is like the total deaths by whatever this is, divided by the total population, like in the United States. And we want to know how many deaths by in an area, and we're going to divide that by the population of that area. We would expect it to be the same, right? It's not really a percent, but we expect the same number of people out of the whole U.S. to die as we would the same number of people in that like smaller scenario, is often what we did here. So to solve for this, we would multiply both sides by that population of the area. So we can answer this question, number of deaths in a specific area, by taking the risk per person that we've calculated. I think it's risk per person, so there should be two pers in there, and multiply that by the population of that smaller area that we're referencing. We also, before we go jump into some problems, we also worked with scientific notation here some. And so when we decide scientific notation, we need to decide like what's the value, like the big value. So scientific notation always has that value times 10 to the exponent. And so to decide that value, it does need to be, I'm going to use some mathy terminology, it does need to be between 1 and 10. And the way this is written, it says it can be 1. That's okay. We don't see it very often. Can't be 10 though. It has to stay a little bit below 10. And this has to be written by moving the decimal point. That's important because it's not so much, I can't just like grab the numbers I want out of there. Like they have to stay as far from each other as they've always been. I'm just going to put my decimal point from however it was in standard form. And so then how do I decide about that exponent? Well, the value for the exponent, in other words, what number is going to go up there, represents simply how far did we move the decimal. Like the decimal point, I guess I should say. How far did we move the decimal point? And this works in both directions, like going from scientific notation to standard or standard to scientific notation. It shows the magnitude change. So how far should I move my decimal, or how far did I move my decimal? Also, we have to decide whether we want a positive exponential number or a negative exponential number. And so if you remember, we use positive exponential to show that the standard form is bigger than 1, like the original standard form number, or we use negative when that standard form number was actually less than 1, some kind of tiny decimal. And so that is a tiny number if we see a negative exponent, or if we have a tiny number and we've rewritten it, we'll use a negative. Or if we want to use a positive exponent, what we're really saying is this is just a positively huge number, right? It could be like 104, and we could put that in scientific notation, but that's really not when we use it. We use it for numbers that are just so big, we can compute them better in that format. So to work some of our test review questions from there, let's start with this number 27, and it has a nice table in your test review, so let's look at it there. The first question asks us, the risk of death by cancer is about how many times greater than the risk of death by diabetes? And so here I'm trying to calculate like how many times greater. So if I want you to think about this, if I said 10 is how many times greater than 5, you would say 2, right? 10 is 2 times greater than 5. And so here we can use that same process of dividing to see. So up here we're going to put deaths by cancer. And then down here on the bottom we're going to put deaths by diabetes, and it's mentioning that diabetes second. It's being referenced by the greater than statement. It goes in the bottom, kind of reviews what we've seen with percentages too. And so from the table it says cancer is 5,900 or 595,100, and then death by diabetes is 83,300. So we're going to divide those two. And we get around 7.1, 7.14. Either of those are great answers there on A. B asks us, what is the empirical probability of death due to diabetes during a single year? And so to calculate the probability of death due to diabetes, you know, we're comparing the death by diabetes here to, because it's the probability to the total population. So that's what we're going to put down here. So number of deaths by diabetes in this chart is, I'm looking in the wrong chart, is 83,300. Good, what we had last time. Divided by the total population here is 453 million. And here it doesn't say by the population in millions, so I can't just take 453. I need the whole number. So I'm going to divide those. Generally, someone asks me here, how do I know that these are not also multiplied by 1 or by 100? Because we have divided several things and then multiplied by 100, and the short answer is simply we're not reporting these as percentages. So I get 0.00018. Okay, so then on C, oh good, practice standard to scientific notation. I'm going to rewrite this into scientific notation. So first I focus on my value. I have 1 and 8. So I want the decimal point between the two of those to get between 1 and 10. And then I do times 10 to the, because this number was less than 1, I'm going to show that it was a tiny number with a negative exponent. And then I have moved 1, 2, 3, 4. I've moved that decimal place to the right 4 to get this form. And so I have a magnitude of 4. So 1.8 times 10 to the 4th. If you live in a city with 35,000 people, how many of those would you expect to die from diabetes this year? Alright, so just like we said a second ago, we expect this to be like 0.00018 is the risk per person for the whole United States. Since this is a risk per person, we can multiply this by the number of people. You hear all that 2A stuff going on in there? We can multiply this by the number of people, 0.00018 times 35,000. To get what we would expect. So we get 6.3, to call that 6 or 7, either one of those is appropriate. It's kind of weird to say 6.3 people, so be careful of that, but either 6 or 7, both are justifiable answers. Because we practiced 2 scientific notation, now let's practice 2 standard notation. So we want to write this in standard notation. So now we're kind of doing the opposite. We're going to have 4 and 1 there. And we're going to need to move the decimal point from where it is 5 places. So we have to decide whether we're going 5 places this way or 5 places that way. Because this is a positive number, that means this is a positively huge value. So we would get that positively huge value by moving the decimal place this way. 1, 2, 3, 4 times. So we had the 1 for the first space, 2. Oh, that's just 4 spaces. I need to go 1 more. 0. So 410,000 is what we get from that value. And you may be thinking, we moved the last one right and it was negative. We moved this one right and it's positive. But remember that left and right only works for one direction. That's why we didn't learn it that way. That's why we learned it as like positive was larger and negative was smaller. And then that thought process would work for both directions. So we don't have to think so much like, does this directly go to right? I can kind of work through the steps between them. And then travel risks. This is the last one we'll work from this section. So it says, 26A says, what's the accident rate per million flight hours in 2004? So we're looking at this 2004. We're looking at the accident rate. We're going to divide it by per million flight hours. So million hours flown. So 26A is going to be 48 divided by 16.2. So we get about 2.96. For B, we're also doing the accident rate per million flight hours, right? Accident rate per million flight hours, but we're jumping to 2011. So that's now 29. For accidents per, I wrote my divide, 17.7 million hours flown. So I'm going to do 29 divided by 17.7, and because they included million hours in the statement, million hours flown, I just have to do 17.7, and I get 1.63, oh, no, 1.64. Right, how about 27? For 27A, oh, those were both A, I'm sorry. Now we're working B. What's the accident rate per billion hours flown in 2004? So we're sticking with accidents. This one doesn't ask us about fatalities, but we're doing per billion miles flown. So now this 48 goes over 6.8. So when I divide those, I get 7 point something. 7.06, I guess we'll call it. And then when I divide the ones for, are we still in 2011? We are. So it's asking us to stick the accidents. So the number of accident rate per, there's my per, billion hours, billion miles flown, that'll be per 7.9. So 29 divided by 7.9, and I typed that weird in my calculator again, so you maybe want to be extra careful you write this if you like me and type weird things in your calculator sometimes. 3.67, and the question is, in general, has aviation become more or less safe from this value right here, our 2004 values, to our 2011 values? So we have lower numbers, which is great news. We want there to be less accidents for every so far distance. So this is looking safer. Good news, huh?